Hey everybody, this is Mr. Ainsworth, and we're going to get into our second family of functions called exponential decay functions, where a is greater than 0. Let's change that, that's a typo. A is greater than 0, it's 1 in this case. B is less than 1, it's 1/2 here. Okay, obviously 1/2 is less than 1. And where the graph is going to be a decreasing function, or in this case, what's called a decay function. And this is totally different than what we did earlier in my previous lesson on the first family of functions, where the base, okay, b here, was greater than 1. We tried base 2, but your homework was base 3. Well, now we changed it to base 1/2. All right, what happens to this function? What does it look like? What's the behavior? What happens to y when x gets bigger? What happens to y when x gets smaller? What happens when you add 2 to the parent function here? And later on down here, what happens when you subtract 3? And, we're going to fix this right here. What happens when you add 1? So fix that. Okay, so we're going to explore these changes here, but the first thing we do is we take a look at our parent function here. We take a look at 1/2 raised to the x power. Okay, the x power here. 1/2 raised to the x. Okay, that 1 and the lead coefficient there, 1, really doesn't affect the function at all. All right, so what we do is we first understand that taking 1/2 to any power can be done. X can be negative. We can take 1/2 to the negative power. We can take 1/2 to the 0 power or to this positive power. X can be anything we want. We've done that before many, many times. X can be negative, 0, or positive, and that's why the domain is a set of all reals again. Okay? A set of all reals. So let's pick some real numbers, some negatives and some 0 and some positives. So here we go. Let's take a look at, let's go from -4, -3, -2, -1, 0, 1, 2, 3. All right, and let's take each one. Let's substitute it into the exponent here, and let's evaluate it. Now, if you write kind of big, no big deal. Take out a piece of paper, do all the arithmetic on the side, all right, and just put the results in here in the table if you want. All right, I'm going to write right here. Just write very small because we got a lot of work to do. All right, we're going to take 1/2 and raise it to the -4 power. And as we learned in class last week when we went over all the exponents, you got to take the numerator to the power and to the denominator to the power. Well, 1 to the -4 power is just 1. All right, and then you got to take 2 to the -4 power. So 1 divided by, we got 1 divided by 2 to the -4 power. As we learned last week in our previous lessons on negative exponents, it just shifts it. Okay, it's in the denominator, so it shifts up to 2 to the 4th, and that's equal to 16. And you should know that because we've been studying powers of 2 so much. Remember, powers of 2, 2, 4, and again, I'm talking about powers of 2, 8, 16, 32, 64, 128, 256, all right, 512, 1024. These are called powers of 2. This is what we practice in class all the time, okay, powers of 2. All right, well, later on in your homework, we did powers of 3. 3, 9, 27, 81, 243, and so on. All right, but these are powers of 2 because the denominators are 2. We're going to take 1/2 now, raise it to the power of -3. And what is that? Well, it's 1 divided by 2 to the -3 power. Again, 1 to the -3 power is just 1. And then 2 to the -3 power, well, that wants to shift up to 2 to the 3rd, and that's 8. Why? Because 2 times 2 times 2 is 8. That's why. All right. Next one, we got 1/2 raised to the -2. That's 1 divided by 2 to the -2 power. That shifts up 2 to the 2nd power, and that's 4. So it's a good thing we did all this development last week because I told you that dealing with negative exponents and fractions is fundamental to the understanding of exponential functions. All right, you can't do this by hand unless you practice the arithmetic way before. So here we go again, 1/2 raised to the -1 power. That's 1 divided by 2 to the -1, and that's going to be, shift that up, that's going to be 2 to the 1st power, or 2. Next one, 1/2 to the 0 power, well, that's an easy one, that's 1. Any number to the 0 power is 1. And guess what that point is right here, 0, 1. Tell the person next to you. Yes, that's right. That's the Y-intercept, okay? at 1 here. You substitute 1 in. 1/2 raised to the first power is obviously a half. The first power doesn't affect it. 1/2 to the second power is 1 over 2 squared, or 1/4. Ooh, the numbers are getting smaller now. Look at this. 16, 8, 4, 2, 1, 1/2, 1/4. The numbers are decreasing on the y values. All right, the y values here, which it represents the range, are decreasing. Y values are getting smaller. That's why this behavior is so different than the previous one, because when the base is 1/2, everything gets its half as big. 8's half of 16, 4 is half of 8, 2 is half of 4, 1's half of 2, and so on. Half is a half of 1. So you can see that the y values are decreasing here. That's why we call it a decreasing or decay function when the base is less than 1, like it is in this example where it's 1/2. All right, you take 1/2 raised to the third power, you get 1 divided by 2 cubed, which is 1/8. All right, 2 times 2 times 2 is 4 times 2, or 8. So you get 1/8 here. So the y values are decreasing as x is increasing. That behavior is totally different than the previous function. All right, and that's how you do it by hand. You can evaluate that on the calculator too. By the way, you can do this right here. Let's go to your calculator here. Let's take the quantity of 1/2, 1 divided by 2, that's 1/2. And let's say we take it to the -1 power. Watch this. Raise it to the -1 power. You get 2. 1/2 raised to the -1 power is 2. How cool is that? 1/2 raised to the -2 power. So 1/2 raised to the -2 power. Look at that, it's 4. That's what I came up with. You can actually get these values on the calculator too if you wanted to. All right, although I would want you to do it by hand first, because guess what? You got to be good, and if you're going to go into higher math, you got to get good at the arithmetic, because that's where it's at, people. Okay, so -4, 16, where is that? So let's start plotting here. Let me see. So -4. Here's -2, and this was -4. -4, left 4 up 16. 2, 4, 6, 8, 10, 12, 14, 16, 18. So left 4 up 16, right there. Left 3 up 8. Left 3 up 8. So that's -3, 8. And this right here is -4, 16. All right, and then we have -2, 4. So left 2 up 4. -1, 2. Left 1 up 2. And our Y-intercept, of course, right there. There's a Y-intercept. Let's highlight that. Okay, there it is, right there. And so the graph is going down now as opposed to up. Oh, it's called a decreasing function or a decay function. All right, again, decay, decreasing. Things are going down, they're getting smaller. That's what decaying is all about. Okay, and then 1, 1/1/2 is right about here. 2, 1/4, right about here. 3, 1/8, right about here. So as you can tell in this function here, it's going down. It's getting smaller. Smaller. Okay, and things are leveling out. And guess what? We have an asymptote here. All right. What is it? Well, tell the person next to you what the asymptote is. You got it. It's the x-axis. It's y = 0. All right. Let's highlight that in red. Okay. There's your asymptote, y = 0. So y = 0, the x-axis here, is your asymptote. You should know that too from linear programming, from all that work we did before on horizontal and vertical lines. All right, so the function is getting smaller, all right, as x gets bigger. Y is getting smaller, okay, as x increases, y decreases, okay, as x gets bigger, y gets smaller. That's totally different than our previous behavior on our other function where we had a growth function. As x gets bigger, look at the table from -4 to -3. X is getting bigger from -1 to 0, from 0 to 1, 1 to 2. Obviously, the x values are getting big here, but look at the y values. They're getting smaller. So x is increasing as y is decreasing. That's a very key aspect of what's called a decreasing or decay function. All right, and that's a key principle in our lesson here. All right, what's the y-intercept? Well, it's 0, 1. It's highlighted already, 0, 1. There's no x-intercept because guess what? It doesn't touch the axis, guys. It's an asymptote. All right, so there's none here. And the range, well, look at this. It's above the y-axis. All these values are above 0. And if all the y values are above 0, guess what? They're greater than 0. All right, so the set of y values, 16, 8, 4, 2, 1, 1/2, 1/4. I don't care how small the fraction gets. It's greater than 0. And that's all we have to it there. So we talked about the intercepts, domain and range, the asymptotes. We plotted the function. And now we back it up with a calculator. All right, so we're going to hit y equals here, or clear out all the graphs. We're going to go quantity 1 divided by 2, and quantity, whoops, I typed it in wrong. 2, you got to type it in correctly, right? Correct input gives you correct output. Remember that. If you press the buttons wrong, it won't give you a good result. Raise it to the power of x, all right, and let's scale the graph. All right, so let's clear out the x minimum. X minimum, let's set it to -6 right here. So -6. X maximum, let's set it to 8. Something less. Here's 10 right here. This is 2, 4, 6, 8. Let's set it to 8 so we can see about that. All right, good. Keep the scale to 1. Y minimum. Well, let me see. It's above 0. So let's set it to 0. And Y max, it's up here at 18, so let's set it to 18. You scale the calculator just like you do a graph, guys. And you just got to think about it. Hit zoom 5 all the time so the axes are the same scale. And so the curve here looks like the same as the curve here. Because the axes are the same, the scale is the same on both axes. So this curve here is the same as this curve here, as you can see it. Asymptote is the x-axis at y equals 0. All right? The other question is, what happens? What kind of effect does this have? What effect does the +2 have on the parent? Okay, on y equals, not 2, that was the previous one, on the parent function, which is 1/2 to the x power. That's the big question. What does it do? We can learn from the previous one. We know what it did on the previous one. Well, maybe it happens on this one too. All right? So we'll check it out. What happens to the offspring when you add 2's to the parent? So go back to your notes on the previous pages and ask yourself what happened before. And maybe it happens the same way again. I don't know. It's always good to test it out, so let's test it out. Let's pick some values here, and let's go for it. So we're going to do the same thing here again. So let's start with -3. So when x is -3, you got 1/2 to the -3 power. So 1/2 raised to the -3 power plus 2. Actually, I'm going to do it over here. 1/2 to the -3 power plus 2. That's 1 divided by 2 cubed, or to the -3 power, plus 2. That jumps up to the top. So that's 2 to the 3rd power plus 2, and that's 8 plus 2, or 10. Ooh, so I'm going to do my side work on the side. Why? Because there's no room in here. All right, so get out a piece of paper, like I said, and do all this arithmetic on the side. Pause the video and go ahead and do that. So -3 comma 10. So -3 comma way up here at 10. Now what happens when it's -2? Now let's figure this out. So -2. Whoop, I got to put it in the right way. I got to put it right up here. So these values, again, go up here in the exponent. So 1/2 to the -2 power. What's that? Okay, so let's go 1 over 2 to the -2 plus 2. This again, the negative exponent shifts it up top, so we get 2 squared plus 2, and 4 plus 2 is 6. And let's get -2 comma 6. Now when x was -3 over here on the parent, we got y equals 8. When x is negative 3 here, we got 10. How is 8 compared to 10? Oh, it's 2 bigger. Holy cow, we're adding 2 to the y values. All these y values are growing by 2, which should make sense here. We're taking whatever 1/2 to the x power is and adding 2 to it. So all y values are increasing by 2. So this is probably going to be another vertical shift again. All right, negative 1. So we got to take 1/2, raised to the negative 1, and then add 2. And it's 1 divided by 2 to the negative 1 plus 2. Shift this up. 2 plus 2 gives you 4. And now we got the next one. So we got 4 here. And if you substitute 0 in, we got 1/2 to the 0 power, which is 1 plus 2, or 3. And then now you start using some other positive exponents. 1/2 to the first power is just 1/2 plus 2. That's 2 and 1/2. We're 2 now. 1/2 to the second power. Let's see here. 1/2 to the second power. So 1/2 to the second power plus 2. I've got 1 over 2 squared plus 2. That's 1/4 plus, excuse me, that's 2. It's supposed to be 2 there. 2 plus 1/4 is called 2 1/4. Okay, so before it was 1/4, but now it's 2 1/4. Why? Because we're adding 2. See what this is it adds 2 to the y values. So if the previous y value is 1/4, well now it's 2 1/4. If the previous y value is 1/8, it's going to be 2 1/8. I mean, it's not that hard to figure out. So 3, 1/2 to the third power is 1/8, as I said earlier, but you're going to have to add 2, and so you get 2 1/8. So you can learn from the past and apply it to the present. Okay, let's graph these. We got negative 3, 10. So negative 3 is right here, negative 2 is here. 10, this is 2, 4, 6, 8, 10. So negative 3, 10. We've got negative 2, 6. We've got negative 1, 4 right here. We've got 0, 3, the y-intercept here. Let's highlight that, okay? That's the y-intercept. That's 0, 3. We got 1, 2 1/2. 2, 2 1/4. 3, 2 1/8. So you can tell they're getting closer to 2 right here, but they're never going to touch it because there's a horizontal asymptote again. All right, the horizontal asymptote is going to be 2 units above because everything's been shifted up. This is a vertical shift up. Vertical shift up, 2 units. All right, before it was the x-axis at y equals 0. Now it's at y equals 2. All right, let's graph that function. Got to go through the points here. All right, so it's a decreasing function here. Y values are getting smaller as x is getting bigger, from negative 3 to negative 2 to negative 1 to 0, 1, 2, 3. X values are getting bigger, y is getting smaller. And once again, that's what's called a decreasing or a decay function. Okay, the y values are getting smaller and they're approaching 2, but they never get close. I mean, they'll never touch 2. They'll just get closer to 2. All these y values, 10, 6, 4, 3, 2 1/2, 2 1/4, 2 1/8, are greater than 2. Okay, and that's why the range is y greater than 2, again, because it's a set of all possible x values. The domain, set of reals, because x can be negative, 0, and positive. So it's the set of all reals here. X-intercept, well, we don't have one because it'll never touch the x-axis, so there's none here. Okay, the horizontal asymptote, like I said earlier here, HA for short, is y equals 2. Horizontal asymptote in my notes is HA. All right, vertical asymptote, VA. All right, and now what does that look like on the graph? Well, I don't know. Let's take a look. Let's compare. All right, so let's enter in the new function and go down to y2, and enter in quantity of 1 divided by 2 raised to the power of x, and let's graph. Oop, it would be nice if I put the right function in. I forgot to add 2. Got to add 2, obviously. So plus 2, that's why we didn't see a new function. And let's graph. There we go. And you know what? I want to graph the horizontal asymptote. We know it's at y equals 2, so let's graph y3 equals 2. Graph it, and you can see it right here. That's y equals 2, up 1 unit, 2 units, boom, there it is. And you can see how the second function approaches it but never touches it. Okay? And then you can explore that on your calculator there. Okay, we're not done yet, so let's go ahead and let's investigate what happens when you change the constant here to, from plus 2 to something else. So let's go ahead and play with this here. What's going on here? Okay, so now what happens when you subtract 3 from the parent function, and what happens when you add 1 to the parent function? Make sure you fix that in your notes, by the way. I should have added the plus 1 on that function. All right, so let's go ahead and set up the domain and range for this function here. And remember, you can take any base to whatever power you want. You can take 1/2 to a negative power, 0 power, or positive power. That's why the domain is a set of all reals. All right, it could be any real number. So let's start off -3 here. And let's start computing. Use the margin for your arithmetic or another piece of paper. Here we go. So I take a 1/2 to the -3 power, and I've got to subtract 3. Now, anytime you deal with a negative exponent, you apply it to both the numerator and denominator. So you've got 1 to the -3 power, which is 1. Divided by 2 to the -3 power minus 3. Anytime you have that negative exponent, all it does is it shifts it to the other side. So it goes from numerator to denominator to the numerator. So really this is 2 cubed minus 3. 2 cubed is 2 times 2 times 2, which is 8. 8 minus 3 is 5, so I get 5 here. On the next one, we got -2. 1/2 raised to the -2 power minus 3. Just look at the function right here. You get 1 divided by 2 to the -2 power minus 3. Every time you see a negative exponent, just shift it to the other side so it goes right up here to the numerator, and you get 2 squared minus 3, which is 4 minus 3, or 1. And then you keep on going. You got -1 here. So 1/2 raised to the -1 power minus 3 is 1 divided by 2 to the -1 power minus 3. Shift it up. That's all a negative exponent does. It shifts it up to the numerator there. You get 2 minus 3, or -1. I'll substitute 0. You take 0, and again, you're taking all these x values and substituting into the x position here. You get 1/2 raised to the 0 power, which you should know is 1. Subtract 3 to get a -2. And tell the person next to you what kind of point 0, -2 is. Okay, it's called the Y-intercept. Okay, it's on the y-axis. So we already know the y-intercept is 0, -2, and we can use that to plot the function here. All right, let's take powers of positive powers. Now, when you have 1/2 raised to the first power, you get 1/2. That doesn't change anything. Minus 3. We know a small minus big is negative, so we know it's negative. 3 minus 1/2 is 2.5, so I know that this is -2.5. So notice that the y values are getting smaller as the x values are getting bigger again. And this is another example of a decreasing, or what's called a decay function. All right, let's put 2 in. 1/2 raised to the second power minus 3 is 1 over 2 squared minus 3. That's 1/4 minus 3. We know that's a negative number because the small minus big is always negative. All right, 3 minus a fourth is 2 3/4, but we know it's negative. All right, so let's plot these values right here as we graph our function. All right, let's take negative 3 comma 5. Here's negative 3 right here. This is 2, 4, 6, 8, 10, 12, 14, and 16. All right, and 2, 4, 6, 8, 10 over here. All right, so negative 3 comma 5 is left 3 at 5. Negative 2 comma 1 is right here. Negative 1 comma negative 1 is right here. 0 comma negative 2 is here. There's your Y-intercept. Again, this is negative 3 comma 5, negative 2 comma 1, and again, negative 1 comma 1, 0 comma negative 2. There's your Y-intercept right here. And let me see, 1 comma negative 2.5, which is down right about there. 2 comma negative 2 3/4 is just under 3, negative 3, or above negative 3. So they're decreasing, but then they're slowing down here, and it's approaching an asymptote again. Because again, watch this. It's decreasing here. Look in blue now. It's decreasing, but what is it decreasing to? These Y values are getting smaller, but they're getting smaller, but not too small, and they're approaching negative 3, but they'll never touch it. Now, negative 3 is right here. So we're going to draw a horizontal asymptote at negative 3. This is Y equals negative 3. That's our horizontal asymptote. You'll see that here in a minute when I go to the calculator. And because again, the Y values are decreasing as the X values are increasing. From 0 to 1 to 2 to 3 to 4, they're obviously getting bigger, but the Y values, well, they're decreasing. That's why we call this a decreasing or a decay function, because they get closer to this but never ever approach negative 3. Here we have an X-intercept here. A little bit tough to find. It's between negative 1 and negative 2. But at this point, it's a little bit difficult to find for you guys. You'd have to have some advanced mathematics in order to figure that out. So I'm just going to say between negative 1 and negative 2. Believe it or not, you don't know enough math to figure that out. So between negative 1 and negative 2. All right, looks like about negative 1.5. Now the range, all these Y values like 5, 1, negative 1, negative 2, negative 2.5, negative 3 and negative 2 3/4, they're all bigger than negative 3 because they lie above it. Okay, so we say that the range, which is a set of Y values, X is or domain is a set of X values. The range, or all these Y values, they're greater than negative 3. So we say Y is greater than negative 3. All these Y values are. 5 is greater than negative 3. All of these are in the range. Again, this is the range, and this is the domain. Okay, keep that in mind. Domain here, range here, they're all greater than negative 3. They're above that line. I mean, it's pretty darn obvious. Okay, and that's how it's done. And so this what happened here is it took the original parent function, which is above here, look at this, where the asymptote is Y equals 0, and it shifted it down, okay? This right here, this minus 3, let's go ahead and denote it here. It's a vertical shift down. Vertical shift down 3 units. All right? And that's what you need to learn from this lesson. The horizontal asymptote shifts down 3 units. It went down, obviously. It was at Y equals 0, but now it's at Y equals 3. The whole graph has the same shape, but it shifted down. And that's what you're supposed to get from the lesson here. All right? X increases as Y decreases. That's the relationship. In fact, let me write it down right now. X increases, all right, as Y decreases. That's a classic case of a decreasing function, okay? So X goes up as Y goes down. All right, take a look at this last function here. And let's take a look at this graph here, and let's plot it, let's graph it, and let's compare. Oh, I forgot. Got to validate this. Let's compare this on the calculator. So let's go to Y equals here. Let's clear out the 2 because it's getting a little bit complicated here. So let's clear them out. Let's go back up to y1. Let's enter this function here. The quantity of 1 divided by 2 raised to the x power. All right, and then minus 3. Now here we're going to have to hit window, and you're going to have to adjust your y minimum because the y minimum and everything else actually needs to be changed. So x minimum, let's change it to about negative 4. Let's change x max to about 8. Let's change y minimum down here at negative 4 and y max up here at 10. That way we can see the same thing on our graph. All right, and let's also, at the same time, let's plot the this horizontal asymptote at negative 3. All right, let me go back to the window. Let's set, yeah, we can see it. You can see here at y equals negative 3, this horizontal asymptote, the function's decreasing here, just like this one here. Hit zoom 5 to square it out, meaning so it makes the x and y axes the same scale, so it looks exactly like ours. All right, it's decreasing and approaching y equals negative 3. This is down 1, 2, down negative 3. All right. Now in this one here, our last one we're going to do, we're going to enter some values in. So let's kind of play with it here. We expect a vertical shift up 1, so let's see if we get it. So let's start off, I'm just going to make it simple here, negative 2. So let's go to the margin here. 1/2 raised to the negative 2 power plus 1. That's 1 divided by 2 to the negative power plus 1. Shift up top, 2 squared plus 1. That's 4 plus 1 or 5. So we get negative 2 comma 5. Negative 1, so we get 1/2 raised to the negative 1 plus 1. That's 1 divided by 2 to the negative first power plus 1. Shift up, 2 plus 1 is 3, so we get negative 1 comma 3. All right, next one. So let's take negative 1/2 to the 0 power and then add 1. That's 1 plus 1 or 2. So we get 0 comma 2. That's a y-intercept there. So we highlight that and we're going to graph that in a minute. 0 comma 2, we already know that already. Next one, 1. So 1/2 to the first power plus 1 is 1/2 plus 1 or 1/2. When x is 2, we have 1/2 raised to the second power plus 1. That's 1 over 2 squared plus 1. That's 1/4 plus 1 or 1 1/4. Okay, and we can graph it from here too. Negative 2 comma 5. Let me see. 2, 4, 6. Negative 2 and negative 4. So negative 2 comma 5 is right about here. Negative 1 comma 3 is here. 0 comma 2 is right here. There's your y-intercept. 1 comma 1/2. 2 comma 1 1/4 right here. All right, so they're getting, the y values are decreasing as x is increasing because we have this decreasing function. All right, however, they're not getting that small. They're getting closer and closer to 1 because, again, that parent function has been shifted up 1. All right, so what we need to do is graph the horizontal asymptote at y equals 1. 1, that's a horizontal asymptote. Let's write it down, y equals 1. Let's compare with the calculator just to make sure we're right. All right. And I'm sure we're right, but let's go ahead and check just for funsies here. And let's clear these out. Let's enter the function in. Quantity of 1/2 taken to the I forgot to change this function here. Everything I just said needs to be modified because I omitted this right here. This is supposed to be just x, not x minus 3. I misread the function. So it's supposed to be to the power of x. All right, here, and then not x minus 3, but just x, and then add 1. Wow, I didn't notice that right there, and that was a typo. It's supposed to be x, just the power of x, not x minus 3. I apologize. Okay, and then go down here, and then the y-intercept or the horizontal asymptote is y equals 1. So let's put that in, y equals 1. Let's graph. So there's y equals 1. Let's hit zoom 5 again like we always do to make the axes the same scale. Notice the function is decreasing and it approaches the horizontal asymptote at 1. Okay, so what's the domain? Well, it could be positive, negative, positive, or 0, so the domain is all reals again. On all exponential functions it is, all reals. The x-intercept, there is none, because it doesn't cross it. Range is above y equals 1, so it's y greater than 1. And there you go. These are just 4 examples of what are called decreasing functions. Once again, go back to your 4th example here and change it. This is a typo, so I want everybody to fix that. That should have been just x, not x minus 3, but just x. I apologize. I'll fix that in your lesson there. All right, and once again, this is a video, so you can go ahead and pause, rewind, play again, hear as many times as you want. I know I go a little bit fast when I teach this alone, but again, this is a video. So go back and redo it, practice on your own, and make sure you do your homework because you're not going to get any good unless you practice. I'll see you in your next lesson. I'll see you then. Have a good one. Work hard and make yourself proud.